In this video, we'll cover the foundations of securing agent workloads that use the Model Context Protocol, or MCP. MCP is an open standard that allows agents to connect to external systems and execute actions. AI agents are increasingly trusted to select tools and execute tasks on our behalf. That means their attack surface is growing too. This video will focus on the core security architecture and emerging threat vectors. To understand and address that challenge, we'll start by examining the core attack surface for MCP-based workloads. Second, we'll detail the representative risks specific to the agentic stack with MCP. And finally, we'll explore the foundational security principles necessary to mitigate these threats. So let's start with the architecture and attack surface. The agent's ability to act is governed by protocols like the MCP. It uses a client-server relationship to delegate tasks. An agent uses MCP clients to handle the protocol-level communication for each MCP server connection. The MCP server is the bridge that connects your agent to various downstream tools and resources. This agent can run on Google Cloud infrastructure like Cloud Run, GKE, or Agent Engine. See the links in the description for each deployment type. And the MCP server could be anywhere and does not need to be on Google Cloud to be accessible to your agent. Now onto the risks. Agents delegate tasks through MCP-based tools. Because of this, a compromise affecting a single tool or its permission set can potentially spread and compromise more of the system. The risks can emerge anywhere on the AI stack. Agents, models, MCP servers, the data itself, and the infrastructure they all run on. So let's take a look at the vulnerabilities MCP may be susceptible to. This vulnerability involves violating the principle of least privilege, leading to overprivileged agents or compromised identities holding excessive permissions. MCPs often grant broad access despite authorization guidance. Malicious inputs hidden within external data cause the agent's reasoning component to execute unauthorized actions via the MCP tools. This expands the security boundary by tricking an agent that was only supposed to analyze content into unintended actions. Agents often aggregate credentials, like OAuth tokens, from multiple connected MCP tools. That makes them high-value targets. If improperly stored, a breach can lead to massive data exfiltration and account takeover across all connected systems. If the MCP server is not securely configured, command injection exploiting unfiltered or untrusted input can lead to arbitrary remote code execution, or RCE, on the hosting environment. To counter these fundamental threats, organizations can use a defense-in-depth strategy. The first part of the strategy is establishing a strong, unique identity for every agent and enforcing the principle of least privilege. This means the agent can only perform the actions absolutely required for its specific task. Anytime an agent attempts to use a tool, there should be a check to confirm that its identity is authorized to use that tool. You can use a dedicated service account, like you would for an application running on an instance. But there's a catch. Traditional service accounts don't always support least privilege. Specialized agents sometimes share the same broad permissions, increasing the potential impact if one agent is compromised. That's where the new Agent Identity platform comes in. Agent Identity establishes agents as a dedicated principal type. This identity is cryptographically attested and bound directly to the runtime, so it cannot be impersonated. In order to authenticate, store credentials in a secret manager instead of using environment variables or hard-coding them. Then, isolate authentication to the MCP client and tool, away from the agent's model or any responses the agent shares with the user's client. In Google Cloud, this is achieved by assigning a dedicated agent identity, or for more traditional workloads, service account, to the agent, which acts as the verifiable identity principal. This agent ID is used as the principal identity in an OAuth 2.0 flow to obtain scoped access tokens or securely retrieve credentials from Secret Manager. This identity is checked by the MCP proxy or authorization server, depending on the architecture. This approach minimizes the utility of tokens in different environments, limiting the impact even if they're stolen. So this foundational control directly mitigates the risk of broken authorization and overprivileged agents by preventing broad access scopes. It also limits the impact of token theft and credential leakage by restricting the scope of any stolen credentials. Defense in depth means creating multiple safety boundaries around agent operations. That way, even if one control fails or is otherwise bypassed, there are other controls in place to limit impact. So the strategy involves deploying agents on confined platforms, or sandboxing, and using runtime tools to inspect data, such as user prompts and model responses. We use hardened deployment platforms like Cloud Run, Vertex AI, or GKE for sandboxing the MCP workload, which confines code execution. Model Armor serves as the critical runtime guardrail. It inspects incoming inputs to mitigate prompt injection, and strictly filters tool call requests to prevent command injection or RCE before they reach the tool. Google Cloud approaches the entire lifecycle of agent security with AI protection and Security Command Center. Now that we have a sense of the representative risks for MCP-based workloads, in our next video, we'll dive into how to implement secure patterns, such as identity, authorization, and runtime protection. Please be sure to see the links in the description for architecture, examples, and documentation. We're always diving deeper, so please comment in the video what you want to see next. Thank you for watching.